is yours.
Good afternoon, everyone. My name is Ashika, and I'm a first-year PhD student enrolled in the University of Szeged, and my research work is based at the Wigner Research Center for Physics. My supervisor is Daniel Barta, and today I would be presenting my research topic, modeling neutron stars in scalar tensor theories. So these are the contents that I would be presenting. So let me start with a brief introduction about what are scalar tensor theories. So it's basically like an extension or let's say a modified version of the general theory of relativity, where we would be having an additional degree of freedom along with the space-time metric, which is a scalar field. So the reason that we choose a scalar field is because it appears in a lot of fundamental theories, like in cosmology or in string theory. And the reason to use the neutron stars were because we were actually trying to test this in a strong field limit. And they are the best one to probe this. And also, we would be able to observe the physical parameters, the change in the physical parameters. So there are two ways to write this theory. One is in the Jordan frame, and the other one is in the Einstein frame. So the Jordan frame is the usual physical frame that we have, where the a scalar field will be non-minimally coupled to the curvature, making the field equations very complicated to solve. Whereas when we turn to the Einstein frame, where actually the scalar field would be non-minimally coupled to the matter field, and the gravity sector is not too modified, except for they would be present as additional sources, making it something very similar to the equations that we have in general relativity and the simpler ordinary differential equations that we will be able to solve. So throughout my work, I have used this Einstein frame action and the potential through which I would be putting up the scalar mass was in the quadratic form. And the class of scalar tensor theory that I've used is the DEF, where alpha is describing the strength of the coupling, and A is called as a conformal factor that helps us switch between the two frames that we discussed before. The equation of state that I have used is APR, which is a realistic EOS for the dense matter. So what is the phenomena that actually happens when we move towards scalar tensor theory is called scalarization. So to know about this, the first thing that we would be required to do is to vary the action with respect to the scalar field. So we get something that's similar to the Klein-Gordon equation, except for we would not be having the physical mass, which we usually have, the physical fundamental mass that we have, but rather we would have something that's dynamically variable, and it's the effective mass parameter, something that is environment dependent. So there are two ways to solve it. One, the solution where it goes to the trivial solution, that is in the general theory of relativity. The next one is where there will be a perturbation. So let's say we are applying a perturbation. So the first case under that would be where this effective mass parameter is greater than 0, then the solution would be such that it oscillates and again gives us the same solution as that of general theory of relativity. Whereas in the case, if it is less than 0, and provided the second term, that is the energy term, is greater than the scalar mass, the solution would be such that it grows exponentially and it leads to scalarization. So we could call this as the actual condition, which is named as a tachyonic instability condition, something that leads to spontaneous scalarization and also change on the physical observables. So the first one that came as an extension to the general relativity was the massless scalar field theory. But it was ruled out later because, as we can see, the decay actually happens as a long-range Coulomb decay by the factor of 1 by r, something that has an infinite range. So the reason that it was ruled out is because when the observations that we check, any observation that we check, so when we look into the data of the orbital decays in a binary system, we know that there is no presence of a scalar field. But due to the long range of the massless scalar field, it actually tells us that there could be a presence of such a field, again, which as we do not see in the observation, so it's ruled out. And then came the massive scalar tensor theory, something that is very short range and almost starts to decay after the Compton wavelength. And it has a limited density window because the energy density has to be greater than the scalar mass value that we will be using. And it is actually consistent with all the observations that we have. This is the space-time metric and the reduced Einstein frame field equations that I've put down. So We could see there are extension to all the TOV equation that we generally have, where there are terms that comes up due to the scalar field. And this is the internal radial profile. So if we look onto the graph on the right, we could see that initially when the instability condition is not met, the graph is actually a kind of oscillating. And then when the instability condition is met, it moves on to decay to zero, something that happens exponentially when the condition is met. So moving to the most interesting part, which is the numerical algorithm. So the method that I have used is the shooting method. For this, we would be requiring an input, which first one is the EOS, which I have used the APR one. And it would be a cubic Hermite interpolator, a polynomial that I have used to interpolate them. And the parameters that that was required are the pressure, coupling parameter, and scalar mass. So as I mentioned that we would be shooting for the value. So it turns out to be a boundary value problem where we would be shooting for two values. One is the metric potential and the other one is a scalar field. So for that, we would be requiring to give some guess values for its central values. And after that, we would be setting up the initial conditions at r equal to 0 based on all the regularity conditions that we have. And then we would integrate these ordinary differential equations based on the LSODA interpolators. And these equations will be cut into two parts where we'll be having the interior equations and the exterior equations. And the exterior equation actually just is different from the interior equation just by the factor that the pressure and the energy density would be 0. So we set the boundary to be around 5,000 because, as I said, we have a limit where it starts to decay after the Compton wavelength. So whatever values that I have used, technically the Compton wavelength comes to around like 1,500. So 5,000 was a good window for that. And the boundary conditions that I set was called as the Robin boundary conditions, where I have used these two particular equations to calculate my residual error. So how do you know the objective has converged, or let's say whether we have obtained our output? So for that, I had used an optimizer called as an algomet, something that's derivative free. So when we are looking for values in different directions, the first thing that we choose is something where we take the derivative and we look into that particular direction. But this one is something that's different, where we would be placing a triangle of three guesses, and the value would be shoot in three different directions. And they also have adaptive step sizes, making them more dependable. And once the objective is converged, which means our residual error had gone to 0, we would be obtaining our output. And I've also developed another algorithm that would give us a better precise radius, something that I would be presenting just after this. So that's called, so based on that, we would be doing the stellar surface extraction. And after that, the stellar surface is obtained by just multiplying it with the conformal factor, which takes us back to the Jordan frame, which is the physical frame. So the improved stellar surface detection. So this is the algorithm where we take a radial profile and we calculate the energy density gradient. And as you can see, the first plot is basically where I have taken only the points where the gradient has a steepest top, and also the points that are almost near to the 0. And I had used a polynomial fit for this to solve the equation such that it goes to 0. And based on that, we could see a significant difference between the two radiuses that had been obtained, one through the pressure, where we obtained the stellar surface with the condition that pressure goes to 0, and the other one with the gradient of the energy density. So this is basically like we are going into a subgrid level. And after that, I have applied moving average and spline interpolation. And I've also calculated the relative radius error so that I could select the points with a less error. And I have finally plotted the graph. We could see a significant difference between the two graphs that are obtained. Sorry, the plots that have been obtained. Yeah. Coming into the main results. So the first one is the mass versus radius. So as we know, the black one is the GR, and we could see a significant raise in the mass and radius. And this is one of the main result of the spontaneous scalarization that is happening. So it is more significant when it comes to higher values of beta, which is the free parameter, and the scalar mass, when it increases, it eventually comes back to GR. So every point on this is basically a stellar configuration for a stable neutron star. The next one is the mass versus central energy density. So the first part of the graph where the energy density is very low, somewhere where the instability condition that I've mentioned is not met, it's somewhat similar to the GR. And with the increase in the central energy density, uh, the we approach towards the limited density window that we have. And the mass actually goes somewhere around 2 times to that of GR and eventually collapses, which is something that's based on the Harrison-Wheeler criterion. Next is about the slow rotation, where I've obtained the graph for between the moment of inertia and mass. So for this case, I have considered the neutron stars to be slowly rotating, which means there would not be any deformity in the star. But in fact, we would be taking only the first order in the star's angular velocity. So the effects of frame dragging would only be present there. And towards the asymptotic region, where the frame dragging would actually be very negligible, is where the spin speed and the relative rotation will actually coincide. And it's somewhere where we calculate the moment of inertia. And as significant, it's a very significant result that we obtained with respect to the mass and radius, because we know there was a significant increase and hence also a significant increase in the moment of inertia. So talking about the technical challenges, the first one was the shooting method degeneracy, because as I mentioned, that with increased value for the scalar mass, we could actually go back to 0. So it required us to use a value which is not too close to 0, but yet something that's around it and where we don't get trapped in the loop of the GR. And the second one would be about the interior exterior stiffness, because different variable varies differently. Some vary linearly, some vary exponentially. So based on that, we required an integrator that, let's say a function that monitors the stiffness. And for that reason, I have used the LSODA function and the pressure zero ambiguity, which I have solved using by going into the subgrid level using the energy density gradient. The next one was the exponential growing mode in the vacuum. So the solution that we have seen, it contains two modes, in which one was the growing mode and the other one was a decaying mode. So the growing mode was only significant when it comes to the need of spontaneous scalarization, whereas towards the boundary conditions, what we needed is a decaying mode so that we would be able to set a proper boundary value. And the next was using a spontaneous scalarization filter. So I used a value for the central scalar field to be around 10 power minus 5, so that we could be properly differentiating between the GR and the scalar tensor theories. And the other one was the main one, where it's a multidimensional shooting complexity, basically a 2D one, two-dimensional one. So it was computationally expensive and very hard and slow to converge. So the conclusion would be that this extended theory of general theory of relativity is actually one of the viable and we could say that it's one of the trustable ones, especially when we are looking at the strong field limits. And we see that a significant difference in all the physical observables that we could have. And the results that I've obtained were quietly, like they match the established literature. And the main thing that I would have done, I could say, is that is to achieve a higher numerical accuracy. And following this, this framework can also be extended to compute the love numbers and tidal deformabilities and any other parameters that we could study neutron stars. These are the reference that I've used. And yeah, thank you.
Thank you for the talk. Is there any question for Ashika? And if everything was clear, then let's move on to our.
Yeah. I have a question. You mentioned two types of approaches of the differential operator in the Einstein equation. What are the observable consequences of the choice? Are there any observable consequences? Which one do you choose in neutron stars?
Do you mean the two frames that I have used?
In the beginning, it was the Jordan frame Einstein.
Yeah, so the Jordan frame is something like It's just like rescaling. That's in a simple way. If I have to explain it, it would be like it's a rescaling. So what we do is that when we use the Einstein frame, the equations that we would be solving would be something very similar to the GR, something we have already solved. So what we do is we calculate the values there, and using this conformal rescaling factor, we bring it back to the physical frame. So it's more like an easy approach.
We still have time for one question. Any other?
Thanks. I would like to ask which kind of precision which kind of machine precision variables were used, like floats or doubles, or even further than the 64-bit.
The 60-bit.
Just have you tried any other type of precision for the simulations, and or did they show any kind of different behavior?
Not exactly, but this is one that I have tried, especially because it's a very computation expensive one. So I stick to the 64.
Thank you.